Okay, so we're going to start with a log base 2 of 7, and we're being asked to simplify. So we're going to say that it equals x, ducky ducks under, we get 7 equals 2 to the x, which can be written as 2 to the x equals 7 if we wanted to. Now, to solve for x, right now that x is stuck in the exponent. We need to get the bases the same, but I can't write 7 with a base of 2. So I need to think of another idea to move the variable out of the exponent. So as I'm thinking, I remember that an exponent can come to the front of a log, froggies can jump off of loggies, so I need to apply a log to both sides. But what log should I use? What base should that log have? Well, technically, the log could have any base, but we want our answer to be calculator ready. Now, most calculators have a common log and a natural log button, so we want to use one of those, and I choose to use the natural log. So I'm going to apply a natural log function to both sides. Now the froggy can jump off the loggy. I get x natural log 2 equals natural log 7. I'm going to divide by natural log 2, and I get x equals natural log 7 over natural log 2. Now let's do that again. Let's try log base 12 of 15 this time. Simplify. So I'm going to set it equal to x. The ducky ducks under. I get 15 equals 12 to the x. And I prefer to switch it around for this type of problem. Now to get that x down, I need to apply a log function to both sides. And which log do I choose? Well, again, I'm going to choose a natural log. I could choose the common log or the natural log because I have buttons for both of those on my calculator. The froggy jumps off the loggy. I divide by natural log 12, and I end up with natural log 15 over natural log 12. I can't reduce the 15 and the 12 because they both have a natural log function being applied to them. It's kind of like a trig function. You can't reduce the arguments of a trig function. My final answer is just going to be x equals natural log 15 over natural log 12. Now hold on to this idea here. We've actually just developed a really important skill, and we're going to come back to it, but I want to go off on a little tangent real quick and show you something else. Let's look back at this problem, and let's say that at this point, instead of applying a natural log, I had applied a common log. The problem would have looked like this. I'd have a log 12 to the x equals log 15. Froggy jumps off the loggy. Divide by log 12. And I would end up with x equals log 15 over log 12. Again, both of the answers that I have found for this problem so far are calculator ready. But let's pretend I didn't care about calculator ready. Let's say from this point, instead of using common log or natural log, I had picked a different base. Let's say I had picked, say, a log base 3. I'd have a log base 3, 12 to the x, equals log base 3 of 15. Froggy jumps off the loggy. Divide across. Our answer would look like this. Let's do that one more time, again with a different base. This time let's pick, I don't know, let's go with say 20. Log base 20 of 12 to the x equals log base 20 of 15. Froggy jumps off the loggy. Divide. And we end up with the log base 20 of 15 over log base 20 of 12. As you can probably see, if we don't care about being calculator ready, it doesn't matter what log base we pick. The pattern ends up the same. It's log base whatever of 15 over log base whatever of 12 for this problem. And this shows what's known as the change of base formula, because all of these answers are equal to log base 12 of 15. The change of base formula basically says that two separate logs that are being divided, as long as they have the same base, can squish together to become one log where the bottom number is the base and the top number is the argument. So this right here would become log base 12 of 15. The bottom number becomes the base, the top number is the argument. Again, the two logs squish together to form one log. The existing bases disappear. The bottom number becomes the base, and the top number becomes the argument, and we would get log base 12 of 15, which is what we have, log base 12 of 15. One more time, the two logs squish together to become one log. The existing bases disappear. The bottom number becomes the new base. The top number is the argument. This would be log base 12 of 15, which it was, log base 12 of 15. Now let's be very clear before we move on. This is where students get confused sometimes. The log property that we know, where division becomes subtraction, is one single log that's being divided. One single log involving division can become two separate logs that are being subtracted. The change of base formula is talking about two separate logs that are being divided. They have the same base, but they are two separate logs. Those can combine into a single log. The existing base disappears. The bottom number becomes the new base. The top number becomes the argument. Now, in my opinion, the change of base formula is more useful to us run in reverse. So if we have log base c of b, we can essentially imagine that two logs have been squished together. So we can now simply pull them apart. We would have log b on top and log c on bottom, and we could put whatever base we wanted to on those logs. In other words, we could choose a calculator-ready log, like natural log, to put on both the top and bottom of the fraction. Now, I'm still asking you to hold on to this skill that we built because it is far more important than the change of base formula. However, the change of base formula comes up, and because it does, we need to prove it. Since this is a proof instead of a derivation, they're going to tell us what they want us to prove. And in this case, they want us to prove that log base a of x equals log base b of x over log base b of a. And this proof starts by saying log base a of x equals something, and we're going to call that m. We're going to convert to exponential notation, so we get x equals a to the m, and it's going to work out nicer if we switch that around. Now, the heart of this proof is that you can apply a log with the same base to both sides of an equation. And so we're going to do that. We're going to apply a log base b to both sides. And now the froggy jumps off the loggy, so we have m times log base b of a equals log base b of x. Now we can divide both sides by log base b of a. So we get m equals log base b of x over log base b of a. But looking up, remember, m equaled log base a of x. So we can now switch our m for log base a of x. And that's it. We have proven the change of base formula. Now again, I show you the change of base formula not because I want you to use it as a shortcut, but because sometimes people throw it around and I want you to know what the heck is going on if you see it. But the skill that we're building of applying a log to both sides of an equation to get an unknown out of the exponent is the far more important skill here. Let's look at a problem. We have 8 times 3 to the x equals 5, and we need to solve for x. We can't just multiply the 8 times 3, don't make that mistake, but we need to get the variable term isolated. We need to get the variable term all by itself. So we have 3 to the x equals 5 over 8. Now we're looking to get this in calculator-ready form. That's the best we're going to be able to do. And calculators have natural log and common log buttons, and I almost always use a natural log. So to get the variable out of the exponent, I'm going to hit both sides with a natural log. I'm going to apply a natural log function to both sides of this equation. Now my froggy can jump off the loggy. I have x natural log 3 equals natural log 5 over 8, and I can divide both sides by natural log 3. So I have x equals natural log 5 over 8 over natural log 3. This answer works just fine. It's calculator ready, but there are different ways to write it. Remember, with logs, division can become subtraction. So we could write this as x equals natural log 5 minus natural log 8 over natural log 3. And that would be a fine answer as well. For problems like these, you need to isolate the variable term first. Try this one. So I'm going to subtract 17. I get 2 times 4 to the x minus 3 equals 42. I'm going to divide by 2. And now I need to get my variable out of the exponent, and to do that I'm going to apply a natural log function to both sides. Now the froggy can jump off the loggy. I have x minus 3 natural log 4 equals natural log 21. Divide both sides by natural log 4. I get x minus 3 equals natural log 21 over natural log 4. And now I can just add 3 to both sides, and I get x equals natural log 21 over natural log 4 plus 3. This is calculator ready, and it is fine just the way it is. Now, if you happen to have the change of base formula rattling around in your head, in theory, we could squish these two natural logs together and make it a log with a base of 4 and an argument of 21. But the problem with this answer is, while mathematically it's accurate, it's not calculator ready, so we don't want to use that as an answer. Let's do another. This time we've got 4e to the x squared minus 2 minus 9 equals 7. See what you can come up with. Now we need to isolate the variable term, which is right here. So I'm going to add 9 and then divide by 4. So I have e to the x squared minus 2 equals 4. To get a variable out of the exponent, I can apply a natural log to both sides. The froggy is going to jump off the loggy, so I have x squared minus 2 times natural log e equals natural log 4. Now, a little alarm needs to go off in your head when you see natural log e. Remember, the natural log function quick sketch is da-da-da-da-da-da-da. It hits right here at 1, it hits right here at e, up 1. And so we're able to say that the natural log of 0 is undefined, the natural log of 1 is 0, and the natural log e is 1. So right here, when we have the natural log of e, that is the same as 1. So what we have is x squared minus 2 times 1 equals natural log 4. Now I can add 2 to both sides. And now I can take a square root of both sides, and when I bring in my own square root, I can't forget the plus or minus. So I have x equals plus or minus rad natural log 4 plus 2. And I kind of feel like I want to check my answer, and I can if I want to, but the original question here is an exponential, and there are no limitations on exponentials. They can be positive, they can be negative, they can be whatever. So both of these answers work. I get x equals plus or minus rad natural log 4 plus 2. I have one more problem for you, and it's a fair bit more challenging. Let's try this. This time we have two variables. I need you to solve for x and write your answer in calculator ready notation. My hints for you on this problem are to use parentheses, distribute, and at some point you're going to want to factor. Try this problem, see what you can come up with. Okay, so here we go. To get those exponents down, I'm going to hit both sides with a natural log. The froggies jump off the loggies. And so I have x minus 2, use parentheses, natural log 5 equals 3x plus 2, again, use parentheses, times natural log 3. And then my other hint was to distribute. So we're going to distribute those terms through. We get x natural log 5 minus 2 natural log 5 equals 3x natural log 3 plus 2 natural log 3. To solve for x, we've got two of them right now. We need to get both x's on the same side. So we're going to use addition and subtraction. We get x natural log 5 minus 3x natural log 3 equals 2 natural log 5 plus 2 natural log 3. And then my final hint was at some point you were going to want to factor. How do we turn two x's into one x? We factor it out. So we have x natural log 5 minus 3 natural log 3 equals 2 natural log 5 plus 2 natural log 3. Finally, to finish this up, I just divide both sides by the natural log 5 minus 3 natural log 3 term. And we get x equals 2 natural log 5 plus 2 natural log 3 over natural log 5 minus 3 natural log 3. We can't reduce any of those 3's or 5's. We're done. That's the final answer right there. More accurately, maybe I should say that's a final answer. Depending on the restrictions they put on the problem, this answer could look very different. Let's say they didn't want coefficients. All these froggies are going to jump up on the loggies. We would end up with natural log 5 squared plus natural log 3 squared over natural log 5 minus natural log 3 cubed, which would then be natural log 25 plus natural log 9 over natural log 5 minus natural log 27. And in theory, we could say that two separate logs being added could become one log being multiplied. So we could change the top to natural log 25 times 9, and two logs being subtracted becomes one log being divided. So we could change the bottom to natural log 5 over 27. This form isn't any more useful than the others, perhaps, so most likely we would stick with the first or second. All right, guys, let me know if you have any questions. Have a great day.